Deep inside a plasma chamber, a wafer is heated, bombarded, and etched atom by atom. And through all of it, it cannot move, cannot warp, and cannot run hot. A mechanical clamp would shadow its edge and shed particles. Instead, the disk turning here reaches up with an invisible electric field and pulls the entire wafer flat against itself, touching it almost nowhere. The hold comes from physics, not pressure. An electrode is sealed inside a high-purity alumina dielectric. Apply a voltage and the layer polarizes, drawing the wafer down with a uniform electrostatic clamp across its whole back. There are no fingers and no edge exclusion. The grip is even from center to rim, so the wafer stays perfectly flat for lithography, etching, or deposition. How strongly it grips depends on how the alumina conducts. Pure, highly insulating alumina above 10 to the 14th ohm centimeters works as a Coulomb chuck, like a charged capacitor. Doped to an intermediate resistivity, roughly 10 to the 9th through 10 to the 13th, it becomes a Johnsen-Rahbek chuck, where charge gathers right at the contact line and grips far harder at a lower voltage. Holding the wafer is only half the job, keeping it cool is the other. The surface is dimpled with thousands of tiny mesas, so helium can flow underneath and carry heat away while the raised tips set a precise contact gap. High-purity alumina shrugs off the halogen plasmas that would erode lesser materials, and it adds almost no metallic contamination to the process. Its talents trace back to a simple oxide. Aluminum and oxygen lock into a dense corundum lattice with their electrons held firmly in place, which is exactly why alumina insulates so well and withstands high voltage without breaking down. The same stable structure resists heat, plasma, and corrosion in the harshest chamber conditions. For a chuck, purity is everything. Raising the alumina content toward 99.99% removes the impurities that would leak charge, seed particles, or contaminate a wafer, and a fine grain under a couple of micrometries keeps the surface smooth and plasma resistant through countless cleaning cycles. The cleaner the ceramic, the more predictable the clamp. Every chamber sets its own format, so each chuck is built to the drawing. Round dielectrics cover wafer sizes from small test coupons up to 300 mm, the dielectric layer itself kept thin, often well under 2 mm, to hold a strong field, while the supporting base carries the cooling channels and connections beneath. Above that base, the working face is engineered in detail. The Mesa pattern and its height set the contact area and the backside gas gap, helium holes and grooves map the cooling path, lift pin clearances match the handler, and the electrode is laid out as a single or split, bipolar design to suit the voltage supply. Nowhere is this hold more vital than inside a plasma chamber, where wafers are etched and coated under intense heat and iron bombardment. Clamped flat by the electric field, the wafer cannot shift or bow as features are cut to nanometer tolerances, while helium flowing beneath the mesas pulls heat away and holds every point at the same temperature. The plasma-resistant alumina keeps the surface stable and the wafer clean, cycle after cycle, with no clamp to shadow the edge or shed a particle. Strikingly, the component that makes the most precise work in the chamber possible is the one the wafer barely touches at all.